Well, I'd like to start by thanking Eduardo and the organizers. It's really nice to be invited here, and Puerto Vallarta is a beautiful place. I'm going to spend some time and try to update you a little bit. I think some of you know what's going on sort of at Telescope Array, but we'll update you on some of the more recent results. Uh, uh, Hopefully. There we go. So Telescope Array is up here, and today we are down here. So we're up in sort of the west central desert of Utah, about 39 degrees north and 113 degrees west. So this is a map of the telescope array. The original part is the green part here. 507 scintillator detectors and 3 telescope stations. And then we added a low energy extension, and we're currently in the process of adding high energy extension out here. So the telescopes are 2 or 3 meter segmented mirrors, and they focus the light onto cameras. 256 photomultiplier tubes are the pixels. There's a UV bandpass filter that goes in front of them, and pixels view about 1 degree of the sky. The scintillator detectors are 3 meters square of active area, 2 layers of half-inch scintillators, and they get read out by wavelength shifting optical fibers that are strung through grooves in the extruded scintillator. So this is what the scintillators look like when they're deployed out into the desert. And here you're looking along the diagonal. You see 1, 2, 3, 4, 5 way back there. So powered by solar power, readout by radio, calibrated by muons. The original array is on a 1.2 kilometer square grid. The low energy extension is 600 and 400 meters, and the new TA times 4 high energy extension is on a 2.08 kilometer square grid. If you were at ICRC, you sort of saw this already. This shows telescope array, the high energy part of the spectrum, and it's compared with these orangish dots, which are the Auger high energy part of the spectrum. And we've long known that there's a shift, sort of 9% between telescope array and Auger. People usually just shift telescope array down halfway, and the Auger spectrum up halfway, sort of 4.5% each. But Professor Oguio said, well, what happens if you modify the telescope array analysis so that you use the fluorescence yield that Auger uses and also use the Auger missing energy correction? And then that yields these red points, which then agree within sort of 1% with the Auger spectrum up until about 19.5, 10 to the 19.5 EV. So that's one way you can do this and get a good agreement, but not at the highest energies. So meanwhile, TA times 4 has been collecting data using the first 3 years of TA times 4 data. He compares his spectrum with Auger, which is the open circles, and the standard TA spectrum, and he gets good agreement with the TA spectrum. That's not going to solve the difference at the highest energies. So one of the things we did more recently is we fit a combined fit to the full Auger spectrum and the full TA spectrum over the full apertures, and that's the red line here. And then on the left, we overlaid the Auger spectrum in the full aperture, and it's not a bad fit. It's a little bit low, as you might expect, because the TA points are higher, the Auger points are lower. If you compare the TA data in the common declination band, there's obviously significant excess over here. The common declination band is this band from -15 to plus 24, 20, almost 25 degrees declination. And that's where you would hope that telescope array and Auger would agree in the spectrum. So this has been studied by Dmitry Ivanov, and what he said was, what happens if we take and divide the telescope array spectrum to two parts, one in the common declination band and the other above the common declination band. And what he finds is that in the band above the common declination band, so the top part of the aperture, the cutoff is higher and the fall off is steeper. In the common declination band, the cutoff looks a lot more like the Auger cutoff, but the slope is significantly different. If you go back and compare what you expect sort of out of the slopes, you expect the slopes to be pretty similar, but just dividing the common declination, the data into common declination band and not common declination band, you get a relatively different slope. These two spectra are different at sort of the 4.4 sigma level, so that's beginning to be significant there. So one thing that we know is that telescope array sees a couple of excesses. One of the excesses is this hotspot, which in the first sort of 5-6 years of data was relatively bright, not so bright more recently, but still some excess there. More recently, there's a lower energy excess, 10 to the 19.4 EV, sort of here overlapping with the Perseus Pisces supercluster. So if you look at where those are in the sky, the hotspot is up here, and Perseus Pisces supercluster is here, and the common declination band is drawn by these two red lines. That's where telescope array and Auger see the same part of the sky. One can argue, and I would, that below this blue line, the aperture, the exposure for telescope array is dropping quite rapidly. And those events are a little bit more poorly reconstructed. The spectrum is a little bit more poorly reconstructed. I suspect that the Auger data at the top of this common band has the same effect. So if we look at what does the telescope array spectrum look like inside the hotspot, inside the excesses versus outside the excesses, and compare them to the Auger spectrum in the full sky. The Auger spectrum in the full sky is these blue lines. Inside you see, as you might expect, a big excess over here in the high energy band. Outside the two excesses, there's still some bump, but they're a lot more in agreement. If we remove those two excesses and then also remove the more poorly reconstructed spectrum sort of below that -5 degrees declination where the aperture and exposure are falling off quite steeply. Now you can see that the telescope array spectrum is much more in agreement with the Auger spectrum. They now agree at sort of the 1.8 sigma level. So this is obviously something that's important, and could be that those excesses are just statistical fluctuations, could be that those excesses are real sources. And at this point, we don't really know. We need more data to actually figure that out. So hopefully most of you saw that telescope array observed a very high energy event. And this is that event. Oh, what the scintillator detector array saw. The circles are the signal in the scintillator detectors, and color is time, size is amount of light or number of particles. This is a huge event, sort of 240 eV. If you figure out where did that come from, well, it comes from someplace right out here, out in the middle of nowhere. There's nothing really out there. You expect these really high energy events to come from something. It doesn't. If you say, well, what if it's not a proton? What if it's carbon, silicon, iron? You compare to different magnetic field models, still you're having a really hard time to figure out what's the source of this. If it's this high in energy, you expect you should be able to find the source. Should be something reasonably close. Meanwhile, we also took all of the events, reconstructed. This is a plot from Toshihiro Fuji at ICRC. The TA events are at the top. TA events above 10 to the 20th at the bottom is the Auger events above 10 to the 20th. And these events don't seem correlated with the distribution of matter in the universe. There was a recent paper that's in the process of being published in PRL and PRD, where our Russian colleagues went through and looked at the events above 10 to the 20th, and they conclude the same thing. That's not correlated with the distribution of matter, or the magnetic fields are wildly different. To make things match, you got to say that things are heavier than iron. So this is crazy. This is something we need to collect enough data and really understand. Meanwhile, telescope array, this is the data. Whoops. This is a little insensitive. Compared to QGS Jet 2-4 protons, nitrogen, helium, nitrogen, iron compared to the data looks light and constant as far as we can tell. Some fluctuations out here where statistics are bad. We also tried doing a composition with a boosted decision tree on the scintillator data, where you have more statistics and you can go out to sort of 10 to the 19.7 or so. And this also agrees with a light sort of proton helium composition. This needs to be better correlated with the hybrid data, but that's what things are saying so far. More recently, we've been doing composition with TA times 4, and this is the result of graduate student Zane Gerber. And again, comparing to QGS Jet 2-4, comparing to protons, helium, nitrogen, and iron, looks sort of right in the middle of protons, helium. Can't really tell what's the difference there. On the other hand, there's a joint Auger-TA working group that they're trying to understand what's going on also. And TA can take the composition, which Auger gives us sort of a mix of protons and heavier elements, and then we can regenerate the Monte Carlo using Sybil in this case, and then reconstruct that data, that Monte Carlo, and compare it to the data. And this is the comparison of those two analyses, the Auger mix reconstructed and the TA data reconstructed. And yeah, maybe they're starting to disagree, but by and large, they sort of overlap in the sky. And so if they're at the same point in the sky, then you got to say, well, how does all this fit together? And I'm still trying to figure that out. So telescope array and also Auger, we both looked for protons and neutrinos in the data. And so far, all we've been able to do is set limits and no photons or neutrinos found. One of the other things that telescope array is working on is starting to deliver some interesting results is lightning. So early on in telescope array, uh, one of the students from Osaka looked at the data and said, there's data in the scintillator that doesn't make any sense. It's all mixed up. It extends over huge amounts of time compared to a cosmic ray. And eventually he figured out these are gammas that are coming out of lightning. So more recently, we've added a whole bunch of electric field measurement devices and some really high-speed cameras, like 40,000 frames a second. And we look at what happens with lightning, and then we look at the signal of what we see on the surface in the surface array. And you can correlate those two. And even now, they're starting to do spectral measurements of what does the light spectrum look like coming out of that lightning at different phases of the lightning as the breakdowns occurring. So this is sort of a side interesting field that you can pull out of telescope array data. So telescope array measures spectrum over more than 5 orders of magnitude in energy. We find a significant difference in the high energy spectrum above and below 25 degrees declination, sort of the common declination band. There's now an 8 sigma difference between the high energy spectrum observed between telescope array and Auger in the full field of view. And the difference in the common band can be reduced to less than 2 sigma by cutting out the data from the excesses and that exposure edge. The hotspot persists, but the significance is not increasing very quickly. It looks certainly a lot less bright. There's a lower energy excess in conjunction with the Perseus-Pisces supercluster. Using QGS Jet 2.4, the composition appears to us to be light and steady, but when we compare to a Sybil generated and reconstructed Auger mix, they look like they're in a similar height in the sky. There's a new high energy event, which is 2.4 times 10 to the 20th. And the thing I really find exciting about that is it's approaching now the energy of the Fly's Eye, oh my God, particle at 3.2 times 10 to the 20th. And observed by, very different techniques, one by scintillators, one by fluorescence. So this is, nice verification that these events do exist. And when we look at events above 10 to the 20th, they appear isotropic. So this is a puzzle that we need to solve.
We have time for questions and comments.
I have a question. You showed that the energy spectra in the hotspots look differently. They have the bump, which is not in the other part.
It's a lot bigger there in any case.
And my question is, did you also look at the X max as a composition in that area to see whether
we have not looked at that, and it needs to be looked at,
Yeah.
although the statistics are going to
Sure,
be
of course,
really bad.
Sure, sure.
But I'm like you, I'm interested in that.
Yes, would be interesting, even though with limited statistics.
Yeah.
Okay, thank you.
Well, it's thanks for a nice talk. I'm very happy to see that when you remove these edges, exposure edges and the excess region, that at least the two of them have come closer together, which is very gratifying. But you mentioned you need to collect more data. Of course, that goes without saying. But really, realistically speaking, given the, you really need a large area, right? So realistically, do you expect with telescope ray times 4 and the present Auger, we can hope to see higher statistics in reasonable future? Or does one really need to make an argument for a maybe order of magnitude increase in area? But that's always going to be the, important
I think,
question.
I think a handful of years with TA times 4 will make a significant difference, but in the end, you're going to really need a much bigger detector. Preferably something that sees both hemispheres. You know, you really got to sort that out.
Thanks a lot, John. Yeah. Now, from my side, I would like to just to sort for myself in my, let's say, view, and also for the audience. So you have the joint working group, and if you could show the slide again.
Which slide?
The joint working group with Xmax, with the depth of shower maximum. Yeah, no, this was already the slide. One back maybe. Oh, forward in your direction, probably. Yeah. That's not, well, I thought you showed it towards the end of the talk. Because I'm interested to see the energy range where we have agreement in the composition. The arrow keys should work, yeah.
This one?
No, the joint working group on Xmax, like Alexei Yushkov et al.
Oh. Sorry, X Max.
This one.
This
yeah.
one.
Because it's my understanding that two collaborations will bring out a paper very soon.
They're trying.
Yeah, let's hope it's going to work. And we do have agreement in the composition in the study, because you see the points are TA points and the histogram is Auger in Xmax. And we do have agreement in the composition up to maybe, I don't know whether the last bin we can say anything about it, but maybe 19.5 in the direct measurement. This is my understanding of this work. Of course, it doesn't mean that we have the same composition at higher energy. That's a different story.
Says you see them at the same point in the sky.
Yeah, no, it's so for the Xmax, of course, I don't know what the sky exposure for TA would be relative to Auger. Maybe then that's an interesting question still to see from what parts of the sky this comes. But we do have agreement now after many years of work, and that's very good disagreement. Both are compatible. And if you now go to the SD data, it looks like we have a large discrepancy in this energy range where we find Xmax agreement.
Yeah.
I only want to point out that this is
This
yeah,
one.
this one. Because in the range of 18.5 to, well, 19 point something, we have almost perfect agreement between Auger and TA, at least what Xmax data concerns. And so what you see is something else, or I really don't know. Yeah. So that part, I agree with you. It's something you need to understand, but at least the fluorescence data, the shower maximum is the same.
Looks like it's in the same part of the
Yeah.
sky. Yeah.
There's the surface data, and then, well, I can tell you that Auger has done the surface data composition analysis, and we are 30 grams off if we use neural networks in Monte Carlo. And we have to calibrate with our fluorescence data to correct for that. We know that our simulations don't describe the footprint correctly. So I would say if you don't do a recalibration or a cross-check of your surface data.
Yeah, and I'm
the
not quite sure.
fluorescence-
I'm not quite sure where that is, and I need
Yeah,
to find that out.
well, for
I've
us,
been
this
trying to.
was- yeah.
Yeah, this is a student that now abandoned. And
Well,
so now I've been trying to find her and get her to answer a few questions.
No, but the constraints.
No,
we
yeah.
also have them in
Yeah.
Auger. It's but I only wanted to say we have to take this with a grain of salt, because
Yeah.
that's coming out of the box.
Well,
But Auger had to recalibrate by 30 grams, and that's a third between proton and iron. It's a big effect. And so you could have a similar thing, maybe to a less extent, I don't know. But you need to cross-check. This
Yep,
is our message that
agreed.
we learned the hard way in Auger. Yeah.
agreed.
Okay, thanks a lot. Yeah, I only wanted to point out that it's
No,
not
yeah.
looking like the two experiments see really different things. Yeah.
Well,
So it's
this-
a little
yeah.
bit more complicated, and so one shouldn't get this impression. But the spectrum is definitely something very, very interesting. We should look at and understand better. And yeah, well, we will have to work on this. Yeah. Thanks a lot.
Thank you, Ralph. Sergey.
Just a minor remark. When you speak about similarities or differences, one has to quantify them. If you please come back to the slide from Yushkov, look at the distributions. Actually, it's not too high energies. No, yeah, right. Look above, not too high energies. In tier data, we see that scalpel events going very deep. They're not many, but they make strong impact on the bits on the sigma X max. And actually, it's a peculiarity of Ajit data. One doesn't see that. There was even a paper from the collaboration initiated by Zigging Group, studying these tails and putting upper limits on